I hope you don't mind if you hear a little background noises. I'm sucking on a candy. Um, Today's topic is a free energy device that for a little while there I um, was doubtful that I did something honest. I thought I was kidding myself. And so I went online and I researched and I discovered something that I already had known about and used in prior simulations of Paul Falstad's simulator, and that is the placement of a load on your circuit to tax it. And when I did that, I couldn't tax the circuit to exhibit any significant loss. I had to strain, I had to really put a huge load on to make any appearance whatsoever show up of detraction from an over unity gain, which was not a big deal because then all I had to do was tweak the parameters of the circuit to accommodate, to offset that loss. And it doesn't take much to accommodate. The funny thing about this, let me see if I'm covering all my bullet points first. Yeah, what I discovered in the course of putting on the loads onto the circuit was the use of an AC sine wave source, voltage source, as a load, and another load to use at the same time is a resistor. And this is when things got interesting. So let me see if I can find the schematic. This is the resistor I put back on, R1 at 5.1 kilo ohms, that I had taken away because I didn't think I needed it. Well, I was operating the circuit without a load. And it turns out, though, a load can do different things depending on where you put it. For instance, what kind of load. In a sense, an inductor is a load. L1 here and L2, those are loads. But the placement of these two inductors here is actually an area of negative resistance. Everything along the midline, the middle portion here, is a negative resistance area. And it defies logic as far as I'm concerned, because this is where all the voltage shows up. And all the current shows up here on the two outer strands and here. Yet it turns out if you put any resistance on these two outer strands, such as I did here, I had forgotten about resistance coming from the aerial going to the starter motor, the starter coils, on an AC motor. Let's see if I can find the right one here. Where are you? Here it is. Now I gotta zoom in. I zoomed in too much. Whoops, still too much. Not enough. There. I took a picture of the motor that I had bought. I had bought an ice cream churning machine, from a thrift store, thinking, oh, what a smart boy I am, last summer, 2018, because it's very hot in Ramona. And it turns out it was missing a part, so it failed to engage the drum in order to turn it. But the motor worked, So I took out the motor and took a look at it, and I didn't understand what I was looking at, so I had to look online to understand that these two pairs of very stout copper, not insulated wire, by all appearance they did not look insulated at all, were wrapped twice around, see here on the outside, and through two holes bored through the stack of laminates. This is, you might say, one of the three orthogonal views of a motor. If we were to look from either side, we'd see these are stacked plates. that go around in a circle, shaped in a square though, a toroidal shape. And we've got the squirrel cage underneath this bracket here. This is a holding bracket. And this is the center part that moves. This part moves, but this bracket is fixed into this hole here and this hole here. I moved it so you could see these wires clearly. Right here you can see just barely the appearance of the squirrel cage underneath this bracket. And the squirrel cage turns freely, and this is one blade of a fan on the opposite side to help cool the thing. And this is one plate that you're looking at of, I don't know, maybe 20 laminate levels or layers that are stacked going away from us, okay? And then there's a bobbin here, a plastic bobbin, that goes, again, through a slot down here, goes through all the laminates, comes back the opposite side, and comes back over to here. And then what we're looking at here is tape, a cloth tape that surrounds the windings. And I peered into the edge here, and I found that it was very thin enameled magnetic wire. I'm assuming it's enameled magnetic wire. But very... This candy is very good. Maple sugar candy. The windings here on this bobbin are very thin and many. I'll say several hundred. You know, an electromechanical water ammeter is under 1,000, maybe 700, 900 windings on the voltage coil. But on the current coil of an electromechanical water ammeter, there's only one set of stout insulated copper wires, and they're wound twice, just like these pair are wound twice. That seems to be the minimum. And as you know, an electromechanical water ammeter, the wires are the coils, the current. I like to call these the current coils because they're very stout wire to accommodate lots of current, not much voltage because there's only a few a few windings. While thin wire wrapped many times encourages the buildup of voltage dominating, as opposed to current dominating in these current coils. Well, these are the starter coils. What happens, the AC comes in here, that's what these red arrows mean. The AC current comes through here, 120 volts, 60 cycles, and all it does is get the squirrel cage to wiggle back and forth, to jiggle, first clockwise and then counterclockwise, and it jiggles every half cycle of a 60 cycle. So 120 times a second, it changes direction. If it were not for these pair of, they are called starter coils, that's all that would happen. But the starter coils are a Tesla invention, and they are induced because the bobbin here of thin voltage, this voltage coil, sets up a magnetic flow in the toroidal stack of laminates, and then that sets up a current flow in these very stout wires. And the current flow throws things off because we only have one over here and one over here, and they're wound a certain way, and they're soldered to themselves to make a closed loop, an electrical closed loop. And that offsets the wiggling such that the wiggling actually will rotate and in always the same direction. And this part I have to take on faith because I still don't get it. But I get it enough to appreciate that this concept of an AC motor, AC generator invented by Nikola Tesla keeps the same themes keep coming up again and again. And that part I get. A voltage-oriented coil of many turns, or many windings if you prefer, a very thin wire, and current coils of just a couple turns, in this case 2 turns, a very stout wire to help encourage the flow of current through this very low Ogg number piece of wire. So this is a standard motor as we have come to know it. And so the current gets induced in these starter double turn windings via the magnetic field flowing through these laminates. There's nothing connected to these. These are connected to themselves to make sure current will have somewhere to go, a closed loop. Talk about fake free energy, you know, because they're living in an environment, a magnetically charged environment that induces current to flow in these closed loop copper wires. Now, we modify it. What we do is we make a special circuit that connects all these coils together. And so I call these coils A1 and A2 because they're associated with the primary voltage source, which is an aerial, A for aerial. But then I realized after I made all these schematics and pictures that my conversation with Byron Brubaker, he had conversations with Joseph Newman saying, you know, you could throw out the battery pack and put in a solar panel, because Joseph Newman had trouble with the dry cell batteries. He was using dry cell batteries that were not designed for rechargeability, and he was wearing them out. Nowadays, you can buy rechargeable batteries, not only NiCads, made it with cadmium, but you can also get nickel metal hydride 9-volt batteries, and I have a few, and I have a charger for them. Well, the Newman motor, besides the fact that it can pump with a lot of torque, you know, rotate with a lot of torque, it also recharges its battery source. Why did I bring this up? But that comes from the large coil in a Newman motor. And the Newman motor doesn't have small current-oriented coils. It could, and when we put them in place of the rotating magnetic field surrounding the rotating bar magnet or permanent magnet on the inside of the large coil, then we have current coils inside the voltage coil. So we don't hook up the voltage coil to a voltage source. We hook up the current coils. And it turns out we feed them very little voltage. My simulations have never been more than 3 volts, and as low as 1.6. I couldn't get it any lower yet. My latest simulation got it down to 2.6, but I understand why. So that's the crux of this video I want to get to shortly. So in this modification suggestion I'm making of an AC induction, single-phase induction motor, we break open these starter coils so they're not closed loops anymore, and you connect them to the circuit. You label them here A1 and A2. They could just as easily be SP1 and SP2 for solar panels. Okay, 2 separate solar panels. You can buy them as toy kits, 1 volt, you know, or comparable from eBay, because that's all you're going to need is a couple of volts. You know, put them in series to give yourself a couple of volts. That's all you're going to need to power this motor. But they go to, in this case, either an aerial or solar panels to pick up the voltage, and then they feed immediately a sine wave generator operating at 1 megahertz. Now the simulation, all my simulations have, both in microcap, which is a variety of spice, and the standard in the industry. They use it at Manitoba University to teach their electrical engineering students electrical engineering in their lab section of their program there. And LT Spice is also used by electrical engineers. For some strange reason, 1 megahertz is the magical frequency, not 60 cycles. Because then you only need feed 2.6 volts rather than 120 or 240 or whatever, 480. But you have to feed them not to the voltage coil, but to the current coils, which are normally called starter coils. And then you have to make this a bifilar winding. You don't have to, but it certainly improves performance. It does not improve performance. In fact, it detracts from performance if you create any more than a bifilar winding, such as trifilar, quadrifilar, and upwards. So a unifilar is not the most efficient, and anything higher than a bifilar is also not very efficient. The magical number is 2. 2 windings in parallel, wired in parallel. So one coil, one end of one coil and one end of the other coil, L1 and L2, will both join up here to the blue line, and the other ends from the 2 coils will join up here to the red line, connected in parallel with the circuit. So, and then it's enhanced with a capacitor. So that's it. You've got the motor, the AC motor that you're modifying, and you put in 2 sine wave generators, 2 voltage sources of very low DC voltage. Very low DC voltage, because the sine wave generator is going to put out the AC sine wave that you normally would have gotten from the grid, when you plug into your outlet. But you create your own, but at 1 megahertz, putting out 2.6 volts. So actually, coming in from the DC source, such as solar panels, or the AC mixed source, such as an aerial, will have to probably be a little higher, than 2.6 volts, because the sine wave generator is going to consume and dissipate a certain amount of energy. But the output from this sine wave generator should be 2.6 going into the circuit. And then you have a little capacitor of 10 nanofarads, and that's it. And then the circuit is simply the arrangement of these parts, the motor with the sine wave generator and the teensy pair of voltage sources, and of course the bifilar coil on the motor, and you broke open the current or starter coils to connect them to the circuit, and a little 10 nanofarad capacitor, and that's it. And this capacitor is a minor improvement, but it does improve efficiency. And so this is the wiring diagram, if I can get this all in one shot here, of the circuit. So here, L1 of 1 Henry now. So that picture I just used as an example, I'm sure it's not a Henry. But this is more comparable to an EV motor, what's inside an electric car. A self-induction of 1 Henry, and an L2 is another Henry. So we have about 2 Henrys on our electric car, but split into a bifilar parallel winding. Here's the 10 nanofarad capacitor in parallel. Now here's a regulating resistor that juggles the ratio between amps and volts that the coils on this thing will enjoy. And I have it set at 5.1 kilo ohms to give me the perfect ratio of 215 amps RMS, 345 volts RMS. Okay? Now here's the starter coil, and I'm assuming, I don't know this, but for the purposes of the simulation, I'm assuming a value of 100 nanohenries. So 100 nanohenries here, 100 nanohenries here, and 1 Henry on each of the bifilar windings here for an AC motor to run an electric car, to be comparable to a 2002 RAV4 EV from Toyota. Their conversion of their RAV4 took out the engine, put in 2 AC motors, and a double battery pack. You see any batteries here? No. You could have a battery instead of the aerial feeding the sine wave generator, but it would be less than your 12 volts, less than the requirement of the 12 volt battery in your car. And I believe, if I'm not mistaken, I can't remember this exactly when I was running this thing, that negative amps will flow backwards to your voltage source, recharging them. So there's no harm done in any source that you use, regardless of whether it's an aerial ultimately, or a small DC battery, or solar panels. There, I'm finishing up my candy. Maybe now I won't make any more noise. This is common ground down here in the lower left. So you see this is pretty much a circular arrangement. It's a closed circuit, and it's free energy in the sense that it's a free boost. Now, I looked up induction motors and electric motors on Wikipedia, and they admit in the article that an induction motor is very much like a transformer. And that's the conclusion I came to, because I'm stepping up voltage from the sine wave generator, putting out a measly 2.6 volts, and this resistor regulating the voltage on these two coils at a nice perky 345. So, but the 215 amps is mostly coming or flowing through the starter coil and the sine wave generator, going back to the sine wave generator. It's mostly on the starter coil. The starter coil has most of the amps, and the voltage coil has most of the volts. And so, but since they're both wound on the same armature, the armature shares both and mixes it all up. The voltage coming from the bifilar winding and the current coming from the two starter coils, it all gets injected into the laminate layers of the armature of the AC motor and gets to influence the squirrel cage on the center. And that's what counts, is the combined influence influences the squirrel cage to rotate fast enough and with enough torque to move an electric car up a hill or into accelerate into traffic on the freeway. Either way, you have to have that much speed and force to get an electric car to move. And my electric car weighs over 3,000 pounds. The battery pack alone weighs 1,100 pounds. So the RAV4 car, in its prior incarnation with an engine, a gasoline engine, weighed a little over 2,000 pounds, but now it weighs over 3,000 pounds. And the Pierce Arrow from 1931 that Tesla demonstrated in Buffalo, New York, weighs in at over 4,000 pounds. So you have to have a massive motor. And this is the beauty of this thing. You can have any amount of energy you want to, and it keeps getting better. Let's say you're not moving around a car, a 4,000 pound Pierce Arrow or a 3,000 pound RAV4 EV from 2002. Let's say you're trying to move around a U-boat, an electro U-boat. During the World War II Nazi days, they had a fleet of electro U-boats, and Tesla gave them his special generator. But let's say we put this in there, and we wouldn't need a whole lot of batteries. Unlike an electro U-boat, usually has to have all kinds of energy sources. Tesla's special generator had to have liquefied air in canisters. They have a diesel engine generator combination. They have to surface to run the generator on the diesel to recharge their batteries. But the special generator that Tesla gave Werner von Braun between 1936 and 1938 in New Mexico, just prior to the war, runs off of liquefied air in canisters. And that runs a piston, and the piston runs the generator. But here, it's solid state, no moving. Well, it's built into the motor. The motor becomes its own generator, because if you need more energy, a silly thing happens. In order to have more volts and amps to run this motor, let's say it's a big, huge 18-wheeler, okay? You're going to be hauling vegetables across the country, and you need more power overall. Well, you increase the size of the motor. Duh. You're going to be doing that anyway. And then you increase the size of your resistor here to match not only the increase of the size of your motor, but to juggle the performance characteristics of your motor. How much amps do you want and how much volts. But that's it. And when you do that, you also have to reduce the voltage feeding the sine wave generator, or else you'll have too much power. And that means your over unity gain keeps going up. The more demand you make on your design considerations of designing the motor to fit the application that you're applying it to. Your gain goes up. It does not go down. That is the beauty of this thing. Now, unfortunately, the windings, this is a huge difference between L1 and L2 and A1 and A2. The difference in not only in inductance, you take the square root of the ratio difference of self-induction between these two pairs of windings, between the current coils, the starter coils, and the voltage coil on the bobbin. You take that ratio and take the square root, and that gives you the turns ratio, which in this case is 3,162 plus a small fraction below 0.5. So I just rounded down to 3,162. And so if you have two turns here on the current coils, then all you have to do is double this number, 6,324 is the number of windings of thin enameled magnetic wire on this bobbin. Twice, though. Each of the bifilar windings has to be that 6,000 number. And you will have outfitted this, and then you connect it, to your circuit. And that's it. That's all you have to do. Now, the coupling coefficients has to be 90% or greater among all four coils. So their ability to transfer magnetic information, to transfer magnetic energy between each other through the laminate layering has to be so efficient that the coupling coefficients, if you're an engineer and know how to compute or calculate what the coupling coefficients is, has to be 90% or greater in order for this idea, this concept to work. And your sine wave generator has to be there at 1 megahertz. So there's certain stipulations, but the benefits to those caveats is enormous. It's truly remarkable that it works at all. Now, let me go back to the tracings. So I did a tracing, and I finally learned how in MicroCap to put in that I want it to spit out an RMS output, because I always want the RMS, since it's an AC sine wave that's rippling through the circuit in all parts of the circuit. And by the way, I have to cover one thing before I forget. One thing before I forget, a very important thing. Here's the schematic, and I put in back EMF on all four coils. And the back EMF I put in is 15%. I don't write it here. Oh, darn. I should have. Well, I'm telling you. Is 15% of the voltage. It's a voltage source turned around, and I have it rated at 15% of whatever the coil adjoining it is putting out. So I think I have 60 volts. See, even though the sine wave generator is putting out 2.6, the starter coils are actually exhibiting a considerable amount of voltage, I believe. Well, let's see. Let's open up. Let's find out, since I didn't write it in to any of my diagrams. Let's find out what I programmed these for. 235 millivolts. So the back EMF adjoining the A1 and the A2 coil is 200 and, what was it? 225 millivolts of back EMF. That's 15% of the voltage passing through this coil. Now, the back EMF on the large 1 Henry coils, the bifilar winding, that was I think that was 60 volts. No, 50. 50 volts. And all 4 coils, I have the voltage source here at 300 hertz, which is double what I expect the RPM of the motor to be. I expect the motor to turn at 150, excuse me, not RPM, hertz. 150 hertz, which times 60, seconds per minute, is 9,000. So I was figuring on an RPM of 9,000, and then I just doubled it. So in case, you know, the motor should be under strain and rotate at 18,000, 18K RPMs, that would be 300 hertz. And that's what I put on all 4 back EMF sine wave voltage sources in the circuit simulation, turned around in reverse to everything else. And I tested it because if I turn it around the other way, they actually step up the frequency of the back EMF voltage sources, sine wave sources, and the voltage. I finally get an appreciable gain or loss depending on which way I orient them. And so I oriented them in terms of loss and then reduced them down to a realistic set of values. But I had to make them extreme to figure out their polarity in the circuit, which way they have to be turned in order to actually give me a certain amount of load to load the circuit. But I figure 15%. And the reason why is because when you run an electric car, you can, at the most, regenerative braking is 15%. You know, that's about all you can get out of a coil. And so I figured, okay, if these coils act as generators of their own, that's what you'll get, is 15% of whatever you are consuming. So I figure my voltage is my consumption when it's running normally without a load, and then I just take 15%. So I look at the coil here, how much voltage is going through it, and then I put 15% of that coming from a voltage sine wave source going in the opposite polarity, and I give it 300 hertz to double the spin rate of the motor. So that I had to cover right off the bat. So now let me go back to the tracings. So I told the software to give me an RMS output, and what I did was, let's go back to the circuit. What I did, sorry, what I did, oh my, it's what happens when you get to be old. Let's see, or talk too much, or both. What was I going to say? I lost my train of thought now. Oh no. Oh, okay. To measure voltage, I took the voltage reading of just one of these coils, L1 or L2, because these are the places that have the highest voltage. The A1 and A2 have extremely low voltage. So I took the voltage of just one of these coils, L1 was my example, and I rated it, and it, you know, it has a surge in the beginning, and then it flattens out very quickly. So in 50 microseconds, I was able to get a very stable RMS reading of 345 volts RMS and 215 amps RMS. Okay? Now, in order to get 215 amps RMS, though, I have to combine the current, the amperage of all 4 coils as a raw feed into this tracing, at which point I then tell the tracing to take the RMS value of the summation of all those 4 values. And that's what I did down here. You see it cut off here. You don't see the full algebraic expression or the functional expression, because these are all functions that the simulator provides as a nice convenience. So I don't have to do the calculations myself and maybe make a boo-boo. So RMS is the function of the current of L1 added to the RMS function of the current of L2 and A1 and A2 over here that was cut off, and then they're added all together. And then you take the RMS of the voltage of L1. Now to do the wattage, you have to multiply this times this and then take the RMS of that. So let's find the tracing for the wattage. Here's it, 74 kilowatts, which is what my car is rated at, a little higher. My car is rated at about 67 kilowatts, so my simulation is right on target. It's pretty close. And just to show you the functional expression here. So you take the RMS of the total product of the RMS of the volts of L1 times the RMS of the summation of the RMS of L1 and the RMS of L2 and the RMS of A1 and the RMS of A2. Now let's see what other, go back to the schematic. So I'll just read to you the text here in case you can't see the text. Dare we replicate Tesla's 1931 Pierce Arrow with an inverted single-phase AC induction motor fed by 2 aerials and a high-frequency sine wave generator, ? Dare we? And I say inverted for a reason, because we're not feeding voltage to the bobbin here. We're feeding it to the starter coils that were never intended to have voltage fed to them, but we feed them high frequency, low voltage, and they work just fine. And that's why I call it inverted. It's turning the wiring schematic of an AC motor on its head, and it performs with greater efficiency if we accommodate it by giving it a higher frequency in the first place. But then we don't have to give it so much voltage, and we save, and we increase the gain just by increasing the size of the motor and the size of this resistor, this regulating resistor alongside the motor. We keep the capacitor at 10 nanofarads for some reason. Okay, continuing on. So R2 and R3, this here of 10 milliohms and this here of 10 milliohms, this is a very important part of this video. They represent a gauge of wire going from the sine wave generator to the starter coils, and that gauge number, that Aug number, is 15, because we want very little resistance. See, there's a very interesting thing, and it's backwards to what I thought originally, but now I've realized what is going on in this circuit. This central portion in here of high voltage, low current, is actually an area of negative resistance, so that anything you do here is a gain. Increase the size of L1 and L2, increase the size of R1 to 10,000 ohms maybe, to match what you're doing here. But mostly here, if you increase the size of L1 and L2, the henries, the self-induction, to anything you want, make it a bigger bobbin, put more voltage windings on there. William Lyons said that on Tesla special generator, I think it was 50 or 100 miles of winding. That's why the lab fire of 1895 really set him back. And we don't have any record of him patenting his special generator. It's a lot of work. And it was arson, because they stole his patent. He was working on a patent, on an invention to give to the patent office on the liquefaction of air. And immediately Carl Linde, Linde, of Germany, patented it, the same invention, immediately after the fire. Well, he gave a demonstration the year before, in 1894, at one of the World's Fairs. I guess it was Chicago, let's say. I can't remember what's the name of the town. And he gave it away, and that's why a year later somebody burglarized his place and stole his patent on liquefaction of air and destroyed everything else, or everything, and so he never went forward with a patent on this special generator as far as we know. But we can increase the size of this the bobbin, the bifilar bobbin, to any size we want to, and we get a gain. It'll keep imbalancing itself, though, and in the direction of too many amps and not enough volts. So then we have to increase the size of this resistor to bring down the volts and bring up the amps so that our motor behaves nicely. And that tells me that this middle area of the circuit is an area of negative resistance. Well, if you use a wire size with a gauge number bigger than 15, exhibiting greater resistance than 10 milliohms, I assumed here a yard at the most, 3 feet of wire between the sine wave generator and the starter coil on the motor. So that means the aerial has to be in the front end of the car, or the voltage source. You know, the sine wave generator and its voltage source has to be at the front end of the car, because I calculated only this is a very tight tolerance here of 10 milliohms, because if you raise this R2 and R3, you actually lose the gain that you would have gotten otherwise on this circuit. So that tells me that this circuit spine here, or branch, this branch of the circuit, this sub-circuit up here and down below, its match, its mirror Siamese twin match, well, not Siamese twin, its twin, are two sub-circuit branches that are areas of positive resistance, because when you raise the resistance, or for that matter, if you do the back EMF any higher in any significant, huge way, that's not very reasonable. But it is reasonable that you could put in the wrong gauge wires, and your sine wave generator might have too much resistance greater than 10 milliohms. All of this has to be 10 milliohms. The voltage source, whatever you use, the sine wave generator, the wire connecting the sine wave generator to the starter coil, it all has to be no more total. You sum it all together, the total resistance cannot go above 10 milliohms, or else you blow the thing and it doesn't work anymore. So that's an area of positive resistance, in which resistance is your detractor. But here, resistance is your friend. And that makes the middle portion here an area of negative resistance. And I learned this many months ago, but I keep forgetting about it, because I don't have the wherewithal to study a circuit like Gabriel Cron could do. And he could tell you, because he knew how to measure a circuit, every single node, he would measure all the different areas of the circuit, and he could tell you what areas are negative resistance, what areas are positive resistance, and he could change them. He could change positive into negative and negative into positive in any section of the circuit. He was that gifted, and his knowledge is all proprietary to the company that he worked for, so we don't know. He did write big books, so if you can read through the books, and I haven't even bothered to, then you can find out maybe what he knows. But so I just have to kind of stumble along, because I don't know how to analyze a circuit to figure out which areas are negative and which areas are positive resistance. I did stumble. The first time I discovered this was when I was designing op-amp circuits in Paul Falstad's simulator, and I discovered an area of negative resistance, and I put a spark gap there, and it improved performance. So if you recognize what areas are negative resistance, you can take advantage of those areas to boost the gain on your circuit, and that's what I've learned here. Increase the size of the bifilar bobbin, the voltage coil, and increase the resistor to juggle, to bring down the excessive amps and bring up the volts, and you've got yourself unlimited gain. Just have to make your motor bigger. Which makes sense, because if you want more power, you'd have to have a bigger motor. So it's so logical. This circuit design concept is so logical, it boggles my brain how we've been doing things backwards all these years. Let's see. I'm reading through this to make sure I didn't... Oh, the chassis of the electric car is the common ground over here. The circuit has to be grounded. Now, if you choose to use aerials, you don't want the FCC knocking at your door and telling you that they have a warrant to take everything, including your socks, your dirty laundry. They'll do that too. Well, come pretty close. Take your toothbrush. They're pretty thorough. They don't like it when people create radio interference in their local environment. Now, people will ballyhoo this circuit and say, "Oh, you think you're getting current from the air?" No, you're not. The aerial, so to speak, is merely a current reference. It's the top load of a modern day Tesla coil inverted, such that instead of immediately adjacent to the top load, you have a voltage coil. Instead, you have a current coil. And so the circuit is creating the current. You're not getting it from the environment, especially if you put solar panels here, just tiny little toy solar panels feeding your car. The voltage, you're running your car on teeny little toy solar panels. I don't think you're getting current through a solar panel from the air, or even from the sun for that matter. You couldn't possibly get that much current. Yet the current will pile up on these outer branches, provided the resistance is low at 10 milliohms tops. And that tells me it's merely a current reference. It is not a voltage reference. It is not a current source. It is a current reference for the circuit. Pile up the current on the outer branches and bunch up the voltage on the inner branch, more or less. But if you choose to use an aerial, it'll communicate with the environment, unlike a solar panel, which won't. And so a solar panel is actually safer, except it'll only run at night. If you use a DC source, you run the risk of blowing up the DC source, like a small battery. So actually scrub that. That's not a good piece of suggestion. Either use a solar panel or an aerial. But if you don't mind driving it only in the daytime, a solar panel is a good way to go because it'll protect you from the FCC. The other way to protect yourself, if you have to go the route of an aerial so you can drive at night, is to use a hollow sphere. Now, a hollow sphere is a very interesting shape. It's very important that we pay attention to the shape of the aerial. It has to have a surface area. That's all it has to have. And a hollow sphere has plenty. It has a surface area on the inside and a surface area on the outside. And it doesn't have to be big and humongous. Tesla had an 8-foot aerial, I believe it was, or 5. I keep mixing it up. I can't remember whether it was 5 feet or 8 feet. Let's say it was 8 feet on the back end of his Pierce Arrow 1931 demonstration. That aerial has very little surface area. By comparison to a hollow sphere, is a very economical use of surface area. We can scale it down, and that's what C. Earl Amon and J.E. Amon, his brother, did in their electric car of 1921, 10 years prior to Tesla's 1931 demonstration. They had but a different shaped aerial. They had 2 bronze hollow spheres placed where the headlights used to be on their car. So they didn't do any demonstration of their car at night, but they had the bronze hollow spheres located at the front of the car. And that tells me they wanted a very short run between the aerial and the circuit of very little resistance. So it's kind of similar to this circuit, but it's probably a little bit different on how it does its thing. In any case, a sphere is a very interesting shape because it's useless for the transmission of radio frequency, because on the outer surface you get cross cancellation and dissipation, kind of like a magnetizable bar of iron in which it is not yet magnetized, and so all the little magnetic dipoles are pointing in random directions every which way. The energy is still there, whether we magnetize the iron bar or not, temporarily. But they're all chaotically arranged, and so we don't get any magnetic dipole unless we magnetize that iron bar. Well, this is the same consideration. Because of the tangential nature of a circle on the outside of a circle, you get dissipation of waves and cross cancellation, but on the inside you get a focal point at the center. And if you open up a circle into a parabola, it now becomes the correct shape to put behind a headlight to cause all of the light beams to go forward in a beam, in a straight beam. But, so a parabola is a circle that has been opened up to create a focal point far away from its locations to create a beam. But when it's enclosed as a circle, the focal point is the center of the circle, and that's where all of the radio interference is going to be emanating into, is the center of the hollow sphere. And so it's perfect for trying to accommodate the FCC and local radios, AM radios, so as not to interfere with their reception of radio broadcasts from various radio stations. So you can be in good relationship with the FCC and not get them angry. Now, C. Earl Lamont used bronze hollow spheres. And I'm thinking to myself, even bronze will tarnish after a while. So I thought gold-plated copper spheres would be best. Now, because I had to ask myself, why are they bronze? Well, that's an alloy of copper. Why didn't he use aluminum? Why didn't he use, well, because aluminum has a higher resistance, and you can't go above 10 milliohms. So you have to keep the resistance down. That's why he used bronze over aluminum. And also aluminum is paramagnetic, which means it makes a great material as an aerial because it tends to tarnish very little, and it tends to dissipate, transmit radio frequency energy away from itself very efficiently because it's paramagnetic, and we don't want that. We want diamagnetic material, which would be copper, and also we want low resistance, which is copper. But gold is also, I believe, gold and silver are very low resistance materials, and gold does not tarnish. So if we gold plate this hollow copper sphere, both inside and out, it'll probably be quite effective. Now, whether or not we have to insulate on top of everything else, the outside or the inside or both, with an insulating layer, I don't know. That's something I can't speculate. I just have to put it out there. That's another factor to consider, to investigate. Let's see. So that was important to cover. I think I covered everything. Yeah, I did. Oh, one other thing. This resistor is a very interesting behavior. Not only does it change the ratio balance between amps and volts when you combine, well, when you look at the voltage on the big coil, because that's the only voltage of any consideration is the voltage of one of the big coils, or the amps of all 4 coils added together, when you balance that, it does something else. And this was a problem I was having. Which one is this? Yeah, not this one. When I had no resistor there, when I took this resistor out, the RMS values tended to wobble all over the place and take forever to try to even out. In fact, they wouldn't. The voltage kept dropping, and I couldn't afford the amount of time that I was spending waiting for the simulator to finish its calculations so that I could make it give me some tracings. I mean, it was remarkably inconvenient when this R1 resistor I had taken out, when it wasn't here. But when I put it back in because I needed to, because I was trying to find ways of balancing the circuit and increasing its gain, a funny thing happened. Very quickly, the values rose to their intended goal, and they took very little time, about less than 10, or let's say no, less than 20 microseconds to significantly flatten out. That's all it took, and then we just get a flat line of RMS, or amps or volts. It's remarkable what a resistor did. It smoothed out, and it accelerated the change in the beginning, and it depressed the surge. There used to be a humongous amperage surge, the red line here. It would go sky high into like 2 kiloamp range and then wiggle its way downwards as it was attempting to flatten out and drop. And then the voltage would not surge as much and would not take so long to flatten out in that sense, but it took forever to flatten out in the sense that it kept dropping. Like, I mean, and I'm thinking, well, how much volts is this thing actually putting out? And I couldn't figure out because I couldn't run the simulator long enough. It's remarkable what that resistor does. It literally helps the thing function better. So you get less surges and you get less droppage over time. The thing stabilizes more quickly, in other words, at its expected levels, whatever it was designed to run at. It takes far less portion of a second, which in real life would not seem like much, but from the standpoint of a motor, every time you turn it on, do you want it to surge to 2 kiloamps? You probably fry the coil momentarily, but you keep doing that. Every time you turn on the motor, it's going to wear out the insulation on the coils. So putting this resistor in here is a godsend. Now it's obviously going to heat up. Everything here is going to heat up, so that's normal. You just deal with that. But it behaves efficiently. The circuit behaves so efficiently, and it's so simple because a lot of the elements here, you don't need them. They're just there for the simulator to be realistic. But wait a minute. But in reality, you need very little. You need the small voltage source, 2 of them, they're independent of each other, feeding 2 sine wave generators, putting out 1 megahertz, 2.6 volts. Then you need your 2 starter coils, you need your bifilar main coil, you need a small capacitor, and you need a regulating resistor, and then you need a common ground, and that's it. The circuit is so simple, it's unbelievable, it's remarkable, and it works, and it's based on time-tested design parameters of an AC single-phase induction motor. And I will leave you with that final note. So if you think there's anything wrong with microcap comes with a lot of kudos, to back it up, and an AC motor. I just do things slightly differently to get these superb results. That's all there is to it.